Okay, hi everybody. We're going to see if we can go through the answers to your practice problems from Friday. So let's take a look right now. It says a student performs a titration to determine the concentration of ethanoic acid in the vinegar using potassium hydroxide. So the question is to write a equation for the reaction in this titration. So what we want to do is we want to go ahead and write out the CH3COOH, and we're going to make it react in the KOH. And since KOH is a strong base, we're going to show this as a reaction that goes to completion, not a equilibrium reaction. So what we're going to have ultimately is the H from the COOH break off and the OH break off. So we're going to make some water, and we're going to make a soluble salt, which means that you can either write this as CH3COOK, or you can write it as CH3COO ions plus K ions. And I recommend that you do the ions personally, because you know that once we get to the actual equilibrium for what is remaining, it's going to be those COO1 minus ions that we care about. So that's going to be your answer for the first one. Okay, so then this next one, the pH curve for the reaction is given there, and it's asking you for you to identify the major species other than water and potassium ions at these points. So by major species, it's meaning what do you have sitting in your container? And let's just remind everybody that we need to know what do we have sitting in the container. And so B pretty much is at the half equivalence point. It doesn't say to identify how much, it just says to identify the major species that you have. So you will still have some acid, CH3COOH. You will also have some OH ions. Okay, you'll also have some OH ions, and you'll also have begun producing the ion COO1 minus, just like that. So that's what you'd have at C. Now, then at the equivalence point where the moles of the acid equals the moles of the base, then you would have to assume that what you have left is really only the what has been produced, and what has been produced then is CH3COO, since we're going to assume that the acid has now been completely used up, and we would have the other thing that is produced, which is the OH that's been produced. So there's what you have going on, and that's what you can expect to find there. Okay, so in looking at what IB says the answer should be, I guess I should have realized that what we actually had going on here is basically some, all of the OH is getting consumed, as in it's becoming part of the water. So so OH and K potassium ions are getting used up, and basically they said not to include the potassium ions and the water. OH and the H are going into the water to make the water, so those should be what your correct answers are. I stand corrected on that one. All right, state a suitable indicator for this titration and use section 22 of the data booklet. Okay, so on this one, I am looking at a suitable indicator, and it looks like I'm needing to look right here, which if I were to look across here, it looks like I'm looking somewhere in the neighborhood of the pH of a 9 at the equivalence point. So I want to be sure that I am looking in the data booklet to find this answer. So let me erase that. Let's go look at the data booklet. And when I go look at the data booklet, I'm looking at something that will change in the range of, that has a range that includes a pH of 9. So this is usually my go-to way to do it, is to look at the pH range. And as long as my my changeover happens that includes the pH at the equivalence point, I am pretty happy with that. So there we go. That's how I choose that one. That means that my answer for this one is going to be the phenolphthalein. So I would write that, just write down for that 1 point is just the phenolphthalein, just like that. And the reason why, if I had to say why, is because it changes in a pH range of 8.6 to 10. And that's our reasoning why there. Okay, so let's go ahead. And notice it also says that they would accept phenol red or bromphthymol blue, but phenolphthalein is the one that is the most obvious there. Okay, so we go on to the state the Ka expression for the ethanoic acid. This is referring to ethanoic acid all alone. So to be able to figure out the Ka expression, we have to be able to write out the dissociation of the ethanoic acid, which, since that's a weak acid, it gets an equivalent equilibrium double-sided arrow. So that means we're going to have CH3COO, 1 minus, and we're going to have H1 plus. And so what we end up with is our Ka expression should be written as CH3COO and H plus, and we're going to have the acid be on the bottom as the denominator. So that's what you should get. Please remember to use your brackets. Do not use the curly or the curvy brackets. Please make sure you use the square brackets. Okay, so then we go on to calculate the Kb of the conjugate base of ethanoic acid using sections 2 and 21 of the data booklet. Okay, so what do they mean by that? Okay, so let's make sure that we understand that the conjugate base of the ethanoic acid is that thing, right? That species right there. And so if we go look at the data booklet, which is what I'd like to do right now, let's go look at section 2 of the data booklet first. Section 21 of the data booklet has the pKa values of ethanoic acid. We have a pKa value right there of 4.76. So I'm going to write that on my screen right here real quick. pKa equals 4.76, just so I have that information. So now I'm going to go and I'm going to go scroll to section 2, and let's just talk about what does section 2 tell me. So section 2, that's section 1, there is section 2. And section 2, I'm looking for anything that might have anything to do with what we are doing. And what I'm noticing is it gives me the ionic product constant there of 1 times 10 to the negative 14. And I'm not really seeing anything else that could possibly be used as a conversion factor. So let me explain how we're going to do that. So it comes down to something that Jake said in class the last time that we were there, and that is, if pKa is similar in calculation to pH, then would pKa and pKb actually be similar in their workings to their relationship of when you add them, they equal 14? And the answer to that question is yeah, pretty much. So let's go ahead and move back to our question. So calculate the Kb of the conjugate base. So if all we have is a pKa, we can do calculating of the Kb. We could say pKb would be then 14 minus 4.76, and then that would give us 9.24 for our pKb, and then we would be able to, working it this way, we would be able to find the Kb as taking 10 raised to the negative pKb, which is in this case 9.24, which when we do that math, let me find my calculator, 10 raised to the negative 9.24, and so we would get 5.75 times 10 to the negative 10. The other way of doing this is calculating this to a Ka value, which would be 10 raised to the negative 4.76. When we do that, we get 1.7 times 10 to the negative 5, which we then would have to find the Kb by using 1 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5. And when we do that, I get the exact same value, 5.75 times 10 to the negative 10, just like we thought. So either way, number 1 or number 2 are options for the way to solve this problem. So hopefully you didn't have very much trouble with that one. All right, going on to our next question. It says in a titration, 25 centimeters cubed, which is the same as milliliters, of vinegar required 20.75 centimeters of 1 mole DM-3 potassium hydroxide to reach the endpoint. Calculate the concentration of the ethanoic acid in the vinegar. Okay, so what we are able to do is recognize that we have a 1-to-1 ratio, and at the endpoint, which is also the endpoint in this case is going to be analogous to the equivalence point because we've chosen our indicator correctly. So that means that our moles of our acid are going to be equal to our moles of our base. And so when we do this, then we are going to want to be able to calculate our moles of our base because we have liters and we have molarities. So we're going to use 0.02075 for our liters. I've converted that to liters, and 1.00 for our molarity. So that means that I have 0.02075 for the molarity of my acid. Okay, and that should be my answer. And let's just take a look real quick. Did we get it right? And in fact, we did get it right because molarity of acid equals molarity of base. Now, so there's that. Okay, I misspoke. What we actually have here is not the molarity of the acid. What we actually have is the moles of the acid. And what we have to do to get our molarity of our acid is we are going to have to take the moles of the acid and divide it by the liters of the acid. So our moles of the acid, 0.02075 moles, are going to have to be divided by the volume of the acid in liters as 0.025. And doing that math real quick, for 0.02075 divided by 0.025 is going to give us 0.83. And there is our correct answer. I wondered if I had gotten that one wrong. Okay, so hopefully you did not make the same mistake I did and you were able to get the correct answer. All right, moving us on to our next question. This one says potassium hydroxide solutions can react with carbon dioxide from the air, and the solution was made 1 day prior to it in the... Okay, so if potassium hydroxide solution can react with carbon dioxide from the air, and you didn't take that into account, but you could have, what type of error is this? This would be the kind of error that is not made better by more trials because you didn't consider that. This is more of a proper set of procedure steps, and that makes this type of error a systematic error, okay? Because it has to do with the procedure steps that you followed. Okay, then we get to the next question. Predict, giving a reason, the effect of this error on the calculated concentration of ethanoic acid. So if OH ions are used by the carbon dioxide, then less will react with the acid, and the calculated concentration will be lower. Let's see if I got that one right. I'm questioning myself. I think that that's what it sounds like. The CO3 would be higher. The KOH would be lower than the value in the calculation, or the larger volume. Okay, there we go. Let me erase what I wrote because apparently I'm wrong. This is what it should come out to. the acid concentration would be higher because okay, I answered in terms of the KOH, not in terms of the acid. So I said the KOH would be lower. Yes, it would be. So if the KOH is lower, then that would lead us to believe that the ethanoic acid is actually higher in concentration than it really is. And then, okay, so the correct answer is there on your screen so you can see how that turns out there. Okay, continuing on. Both vinegar and bleach are used as cleaning agents. Outline why ethanoic acid is classified as a weak acid. Hopefully you said that it only partially dissociates. Okay, hopefully that is what you said, that it only partially dissociates. And that is the correct answer. Suggest with reference to Le Chatelier's principle why it is dangerous to mix vinegar and bleach together as cleaners. Okay, so if this is our equilibrium equation right here, here is our equilibrium equation, then what we want to do is recognize that if vinegar is used, then the bleach, let's see here, bleach can react by reacting chloride gas. So, and you know, I'm questioning myself. I was thinking if vinegar is used, what they're asking, why would this be a dangerous situation? So we would be taking bleach out. But I'm wondering if that means that we are going to, if the bleach is going to react with, let's see what it actually says. I want to know what this says myself here. So we are going to scroll down and take a look at the answer. Ethanoic acid reacts with NaOH. Oh, we are not reacting the bleach with the vinegar. Then what we are actually doing, if vinegar is then going to react with the NaOH, it will make more Cl2, which is a toxic gas. Let's see if we got it right now that I've got myself thinking in the right direction. So moves the equilibrium to the left or releases the Cl2 gas, and it is toxic. Okay, so that is what we were getting at there. I'm not going to ask this type of question on your quiz, but just so you know, IB is likely to ask that kind of question. Okay, so here we are. Sketch a graph of pH against volume of hydrochloric acid added to an ammonia solution, showing how you would determine pKa. All right, so hydrochloric acid is the titrant. It is in the puree, and the ammonia solution is being titrated into, it is in the beaker. So that means we have to recognize what we have. We have hydrochloric acid is a strong acid, ammonia solution is a weak base. So that means that we are going to start with it somewhere around, and I'm going to guess that this is somewhere around 10 to 11. And we can generally say that it is going to drop, and halfway down the vertical rise, we would expect that value, since this is strong acid, weak base, we would expect the halfway to the equivalence point to be below 7, and we would have this end down here. So I'm going to label this as a 1 so I can show my strong acid. I'm going to label this as a 10 to show my strong base, and that means that my pH at the equivalence point would be below 7, and I want to be able to show that being below 7 as well. How would you determine the pKa of the ammonium ion? I would use the half equivalence point, because at this point pH is equal to pKa. So I would use the half equivalence point and measure the pH, which is going to be slightly lower than 10 at that half equivalence point. You might argue that it should be a little bit further, and that's fine, but you would need to have something like this to show. And then I wonder if it gave us space to write down here too. It did give us space to write as well. So you would want to also use some words to describe what is going on there, just to be absolutely sure. Let's take a look at what did they say for their answer there. We have yes, we have the pKa being identified, and we have, so the volume would be half of the volume there. Then they did not identify the half equivalence point, but we did pretty good, I would say. Correct shape of the graph and a vertical drop. We would also have pKa equals pH at the half equivalence point. I think we did pretty good on that one. All right, next one. Suggest a suitable indicator for the titration using section 22 of the data booklet. So if we are talking about a pKa that has to be below 7, then we would want to go to the data booklet, and I'm trying to scroll right back here to section 22. I'm already at section 33. There we go, acid-base indicators, and I would want something below 7. So I would pick either a methyl red, or a bromcresol green, or a bromthymol blue. I wouldn't want it too low because methyl orange would be down near where it starts getting into all acid territory. So I would pick one of those 3. So let's go see how right we are about that. All right, suitable indicator, methyl orange, bromthymol blue, bromcresol green. They even picked methyl red as a possible choice as well. Okay. This next question, which combination of acid and base is most likely to have a pH greater? So let's label this. This is a pH greater than 7. And you know that a pH greater than 7 is the combination of a weak acid with a strong base. And so we need to go find a weak acid and a strong base. So I'm going to label things. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. Hydrochloric acid is a strong acid, and ammonia is a weak base. Then we have nitric acid is a strong acid, and ammonia is a weak base. Finally, we have a weak acid and a strong base. So D, as you can see, should be our correct answer there. Okay, this one says butanoic acid, listed there, is a weak acid, and ethylamine, listed there, is a weak base. State the equation for the reaction of each substance with water. So I'm going to have butanoic acid, CH3, CH2, CH2, COOH, plus some water is going to make me, it has to have its equilibrium, and so we're going to have CH3, CH2, CH2, COO1 minus, and we're going to make the hydronium ion H3O1 plus. The ethylamine is going to be CH3, CH2, NH2. In this case, it's going to react with water, so that means water is going to get to act as an acid and donate the hydrogen, so we're going to end up with CH3, CH2, NH2, whoops. Okay. NH3, it's going to have a 1 plus, and we're going to have an an OH remaining. So those are going to be our 2 reactions there. Okay, very nice. That is what we got. I love it when I get the right answer. It's very nice. Okay, so then it says, a 0.250 mole DM-3 aqueous solution of butanoic acid has a concentration of hydrogen ions of 0.00192. Calculate the concentration of hydroxide ions in the solution. All right, this one is only 1 mark because it relies on you remembering that 1 times 10 to the negative 14 is equal to the hydrogen ions times the hydroxide ions. So you, to get your hydroxide ions, should only have to do 1 times 10 to the negative 14 divided by the hydrogen ion concentration is 0.00192. So to be able to find that, we're just going to use our math real quick. 10 raised to the negative 14 divided by 0.00192. And I'm getting 5.2 times 10 to the negative 11. I'm getting 5.2 times 10 to the negative 11. And they're getting, oh, I know why. I have an extra. I should have had 1 raised to the negative 14, not 10. So my math was wrong there. So that is a calculator issue on my part. That was a bad deal. Okay, so that's what you should have gotten for your answer. That should have been that easy. All right. Determine the pH of a 0.250 mole solution of aqueous ethylamine using section 21 of the data booklet. So that means that they want you to go look up the pKa or pKb of the ethylamine. So let's go see what we find in the data booklet right now. This is section 21 when we're looking for ethylamine, and there it is right there, and that is giving us a pKb of 4-ethylamine 3.35. So this is actually going to be 3.35. That will give us some necessary information there. And I'm going to erase these two things right here so they don't show up. Let's go back to our page. Okay, so it says determine the pH of this solution. So let's remember what we have on our equation of ethylamine is CH3CH2NH2, and we have it reacting in some water. And we are going to, and I'm just rewriting it again so you can see it. We're going to end up with OH ions and CH3CH2NH3. Okay, so it's saying that what is this pH? So the initial concentration is going to be 0.25. We don't care about the water. We'll have 0 of this and 0 of this. We're going to have minus this and then plus X and plus X. And so ultimately we will have 0.25 minus X, which we will negate. So I'm going to have KB is equal to X squared over 0.25. And so I just need to do 10 to the negative pKb to find my KB. So KB is going to be, oh, I've got to clear my calculator. Hang on. So I'm going to end up with 4.47 times 10 to the negative 1, 2, 3, 4. 10 to the negative 4. So setting that up, I'm going to have 4.47 times 10 to the negative 4. Solving for x after multiplying and then square rooting. So times 0.25. And then I'm going to square root that answer, getting x is equal to 0.011 for my x, and my x is equal to the hydroxide ion concentration. Now that's not my answer because I was asked for pH. So now I'm going to find the POH, and POH will be negative log of 0.011, and so negative log of 0.011 is going to give me 1.96. So that means pH will be 14 minus 1.96, which 14 minus 1.96. So 12.04. So hopefully we got that one right. That'd be great if we got that right. There we go. And pH 12.04. Yay. Let me erase everything that you see here so you can see what the mark scheme actually says, so that you can take a look at that, what IB actually says it should come out as. And I think we did the right thing. You can see where the check marks are to see where the actual points are awarded. Basically, you just get all 3 points if you get the correct final answer, but showing your work is always helpful. Okay, onward we go. 4D, sketch the pH curve for the titration of 25 centimeters cubed of ethylamine solution with 50 centimeters cubed of butanoic acid of equal concentration. No calculations are required. So this is where I always get confused, and you might get confused too. I am going to assume that what I see here, sketch the pH curve for the titration of 25 centimeters cubed of ethylamine with 50 centimeters cubed of butanoic, and they're both of equal concentration. So we're not going to have any calculations that is going to go with this. but I'm going to assume that that means ethylamine is going into the butanoic acid. So that's my assumption going to be, and then we're gonna see if we are correct or not. Okay, so let's take a look here. Okay, instead of drawing it, I decided to show you what there is here. So they did it the opposite way. In this case, they were having the butanoic acid going into the ethylamine. And I think what would have been the clue to figure that out, did you notice that the question stem had more volume of butanoic acid than volume of base that it was being used? And so that would have led us to the complete titration here, starting at, of course, the lower but still basic pH. You'll notice that what we don't have, what we have seen mostly prior to this, is we've seen this kind of thing with a strong thing, and then us come down here more like that. And that is what you're not seeing. And what we have going on, what this question was about, was a weak base being titrated with a weak acid. And when you look at the notes that they have for this, you'll see some of the thinking here. It's a decreasing pH curve. pH close to 7 because you have weak acid, weak base. They don't know for sure that it's going to be a pH of exactly 7, but somewhere around close to 7. So in the neighborhood of 6 to 8. So this is a weak acid-base shape with no flat, strong acid-base parts on the curve. In other words, you notice there's no plateaus. It is still a sloping line in all cases. For this reason, I'm really glad I didn't ask you to do this on the quiz, because I don't like this question very much. And I know they don't use this question very much either. Okay, so let's continue on. Then it's which indicator is appropriate for the acid-base titration shown below. And so it's asking you for thymol blue, methyl orange, bromphenol blue, or phenolphthalein, and all it's giving you is the pKa's. And so as long as you pick the pKa, I think it was a -1, pKa -1, then within to get the equivalence point, then you should be okay. So the equivalence point, we are starting at 12 and ending at about 5.5, and we started at about 12. So halfway between that's a difference of approximately 6.5. So halfway in, is that right? 6.5? Yep. So that means you're going to need to go approximately 6.5 down from 12. That is 6.5. So approximately 3.35. So we should be somewhere around right in this neighborhood right here. Okay, so that means we need a pKa that is going to be -1 somewhere in that neighborhood. So that means we should pick phenolphthalein for this one. All the other ones are just way too low. They would all change. The pHs of all of these would all change somewhere down here, and our equivalence point is way up here. So this one, the D, is the better correct answer choice. Okay, which titration curve would occur when a weak acid is added to a strong base? So that means we're starting with a strong base, and we are adding a weak acid to it. So you would expect the strong base to hang on to its flat line a lot longer. So strong base is identified by starting at 14. This one is wrong because that would be more like a weak base. This one would be wrong because that is more like a weak base. So B or C look good. And then we have when a weak acid is added to a strong base. So we would have to have the format coming out to a weak acid, and this is much better as a weak acid, whereas this one is much more like a strong acid. Cross out C, correct answer B. Okay. Number 7, the concentration of a solution of weak acid such as ethanoic acid can be determined by titration with a standard solution of sodium hydroxide. Distinguish between a weak acid and a strong acid. Hopefully you say, just like it says below, that a weak acid only partially dissociates, whereas a strong acid completely or 100% dissociates. Then number 7b, Suggest why it is more convenient to express acidity using the pH scale instead of using the concentration of hydrogen ions. Hopefully, you recognize that it's a simpler or easy way to do it. It results in too wide a range of numbers, and so this converts the exponential expression to more of a linear scale. So one of those is a better choice there. So let's go on to the next part here. All right. 7C, 5 grams of an impure substance of hydrated ethanoic acid, which is given as that formula right there, was dissolved in water to make a 1 liter solution. DM3 is a liter solution of 20. If 25 centimeters cubed samples of the solution were titrated against 0.100 mole DM-3 solution, that's a molarity of sodium hydroxide, using a suitable indicator. There's the equation. It gives you then the mean value of the titer was 14. So this is going to be the volume at equivalence point. That's what that mean value of titer means. It means they've done several trials and they found the average or the mean value of the volume at the equivalence point. First, it wants us to calculate the amount in moles of NaOH that is needed. So let's do that. So I is going to be moles will be equal to molarity times liters. So we are going to do molarity 0.100 times liters, and remember to change our 14 centimeters cubed to liters. So I'm going to get 0.0014 moles of NaOH. And then double I is going to be calculate the amount in moles of ethanoic acid in each 25 centimeter cubed sample. Okay, so first thing we have to do is find the molarity, and the molarity is going to be 5.00 grams. We're going to need to divide it by its molar mass. So to get its molar mass, I'm going to add 2 times 12 plus 16 plus 16 plus 1, and then I'm going to add 2 times water's molar mass, which is 18. So to get that, I am going to 12 plus 16 plus 16 plus 1, multiplying that by 2, and adding to that 18 times 2 is going to give me, my molar mass is 126, so I'm going to divide this by 126, not 129. And then to get the volume, I'm going to divide it by the 1 liter. So I end up with 5 divided by 126, which my molarity is 0.03968, so I'm probably going to end up with 0.040 for my molarity. Now it's asking us to find the moles in each 25 milliliter solution, so I'm going to have the molarity times the liters, and the liters in this case will be 0.025, so times 0.025, and I'm going to get, let me make sure I do that right, 0.04 times 0.0, and I'm getting 0.001 for my number of moles of acid. Okay, and then it says calculate the percentage purity of the hydrated ethanoic acid. I think I took this part off of it. The percentage purity of the hydrated ethanoic acid. We're going to go down to the bottom and take a look at how did you do that. So let's go ahead and take a look at the answers according to, okay, so we have, all right, we have 14 times this, so we got, that was correct, we did that one correct, and then we did 1/2 of 14, so they ended up with that, and we ended up with, that was moles, and they did it differently. Let's see here. Okay, they ended up getting what we ended up getting there, pure hydrated. All right, so it looks like they did things differently than we did it. So here is the number of moles. That's what I got for the number of moles, actual amount hydrated, which would have been multiplying that by moles. And there. I'm looking at how they did it, and I'm kind of concerned about how they did it. I'm going to leave that on the screen so you can see all of the answers there, so you can see all of the different ways it can be solved. I have a big question mark in my head about this one, so I'm going to leave you guys to take a look at that one. A student wished to determine the concentration of solution of sodium hydroxide by titrating it against aqueous solution of hydrochloric acid. Okay. 4 grams of sodium hydroxide pellets were used to make a 1 mol DM aqueous solution. 20 centimeters cube samples of sodium hydroxide solution were titrated using bromphimol blue as the indicator. Outline giving your reasons how you would carefully prepare the solution. So I would, so let's just look at what IB would like you to see. Key procedural steps: use a volumetric flask, mix the solution, fill up to the line of the mark. Use the balance that reads to 2 decimal places for the mass. Mix pellets in the beaker of deionized water and stir with glass rod. Use a funnel to avoid the loss of solution. So just really common sense sort of things here. Okay, state the color change of the indicator that the solution would see using this titration. All right, so it said bromphimol blue. Yeah, so let's go look at the indicator. Bromphimol blue. Bromphimol blue would change from yellow to, let me make sure that we know, is it going to change from yellow to blue because we're in the acid, or the other way around, from blue to yellow? Let's see here. The student added the acid too quickly. Okay, so the acid is being added. So we're going to start with blue and it's going to change to yellow. State the color, blue, and then to yellow. And then it says, outline giving your reason how this could have affected the calculated concentration. It would make it seem too high because you added too much acid. Yep. Okay. Suggest why, despite preparing the solution and performing the titrations carefully, widely different results were obtained. It is a color differential. Yep, using different hydrochloric standards. So lots of different ideas on how you could have messed this whole thing up. Okay, everybody. I hope that was in some way helpful.